Good morning, and welcome to Miss Bowman Teaches You Asynchronously again. So today I'm going to be going through the first day's notes on the Unit 3 packet. So if you have your packet collection, we're going to be starting Unit 3. You just took your Unit 2 Concept of the Derivative exam, so congratulations there. And we're going to be starting with kind of going through some simple derivatives here. This unit is focusing on the algorithm of the derivative and kind of the rules for differentiation. So now that you know what the derivative is and what the derivative means to us and what it tells us about a function, now we're going to be focusing on all the different types of ways to find the derivative of a function and generalizing the limit process so that we no longer have to kind of do it. So I want you to pause me right here and then try to find the derivative, f prime of x, the derivative function for each of the following f of x's. Many of these we've done in our previous notes, but pause me and take about a minute or so to kind of go through and think, what would the derivative be here for each of these functions if we used the limit definition? Okay, so now that you've had a chance to think about it, let's go through a couple of them. So if f of x equals 17, that means that function, if I were to think about that function is just a horizontal line at a height of 17. Its slope is always 0, so f prime of x would equal 0 here. If I had f of x equals 2x minus 5, 2x minus 5 is a linear function with a slope of 2. Which means that every point has a slope of 2, and the derivative here would be a constant 2. Now, f of x equals x squared, that's what we've done. If we were to go through the whole process here, we would find out that the derivative function for this one is 2x. X cubed we've also done. The derivative of that function is 3x squared. Okay, so now let's talk about what might happen with this 5. Now this is a quadratic function, x squared minus 3x, but really I'm going to think about this as being two different functions, a quadratic function with a linear part. Now if we remember from limits, since the derivative is just a limit, if I take the limit of each piece and subtract them, that would be equivalent to finding the limit as h approaches 0 of the whole thing. So this derivative would be 2x minus 3. Okay, so let's see if we can't think through what's happening in each of these derivatives. So we're going to go through a couple basic rules here, and I'll probably be jumping back and forth between the page. So rule 1 for derivatives, if we have a constant function, if I want to take the derivative, remember this is the command form, of some constant, that derivative is always 0. So if I have f of x equals 2, f prime of x is 0. If I have g of x equals square root of 3, g prime of x is 0. If I have h of x equals pi, h prime of x is 0. If I have y equals e squared, notice that e squared is a number raised to a number. That is a constant, folks. There's no x in that expression. So here, y prime would still be 0. So there's your first rule of derivatives. The derivative of a constant is always 0. Okay, let's talk about another rule. Rule 2. Now, let's go back and see if we can't make an observation. If we look back at number 3 and number 4, you guys have already started imagining here. When we were talking about this last unit, you guys were like, isn't it just 1 degree less when we take the derivative? Yeah, and in fact, if I really look at what's happening from x cubed to 3x squared or x squared to 2x, imagine for a second I gave you the function x to the 4th. Could you imagine what the derivative function would be there? And if you said 4x to the 3rd, you're correct. So we can see when we have a polynomial function, so when it's x raised to a constant number, that all we're doing is bringing the exponent down to the front and then decreasing the degree by 1. So if I were going to generalize that, if I have x to some power, x to the n, the derivative function is going to be n times x to the n minus 1. So the exponent becomes the coefficient, and then the new exponent decreases by 1. So if g of x is equal x to the 20th, then g prime of x would equal 20 x to the 19th. Welcome to the power rule. No more limit. Can you imagine trying to do x plus h to the 20th power? That sounds insane. So we're just going to apply the power rule anytime we have a polynomial function. Now the constant multiple rule is going to be our third rule here. The constant multiple rule is talking about when we have a vertical stretch to a function. So let's call k a constant. Okay. And let's say we're taking the derivative of k times some function. So we have vertically stretched that function by a factor of k. If that is the case, if we vertically stretch a function, we have stretched the rise without stretching the run. That's going to stretch the slope. So all the slopes are going to be multiplied by factors of k. So this would be equivalent to saying k times the derivative of f of x. Or we could say it's just k times whatever that derivative function is. So if we have a constant multiple, we're just going to take that constant multiple times whatever the derivative is of the function. So we'll do an example of that one. And I know I'm going through these rules pretty quickly. One, because I feel like you can handle it, but two, just pause me if you need some time to think about it. And I'll show you what I'm not going to do from here on out. But for example, if I have 11x to the 9th, 11 is what we call a constant multiple. It's a number that's being multiplied and vertically stretching the x to the 9th. So when I take the derivative here, I'm going to show you the very long way, okay? It would just be 11 times whatever the derivative of x to the 9th is. I never need to see this step, but you need to understand that this is technically what is happening here. So then I would end up with 11 times, and if I find the derivative of x to the 9th, that is 9x to the 8th. Okay, which, if I simplify that function, would become 99x to the 8th. Okay, so technically, this is what's happening. That doesn't even look like an 8. Okay, now a lot of you are like, can I just take that 9 and multiply it by 11 or whatever's in front? Yes, absolutely. You could have just written 99x to the 8th and been done with the problem. I didn't need to see those two steps in between, but I need you to understand that those are what those steps are, so that when we were given a case where we have to apply this rule theoretically, we understand what this rule is telling us to do. Okay, now the sum and difference rules I kind of hinted at the beginning of class. The sum and difference rules here, I know I'm going through a lot of rules. Again, I think we're going to end up doing maybe just these 4. Maybe there's one more. I can't really remember. It's Indigenous People Day. If you're wondering what I'm doing today, I'm filming all these lectures for you and putting them on the YouTube. Okay, so if I was going to take the derivative of two functions that are being added or subtracted, and there's a nice proof of this if you want to see in your Fedowalk book of why this works, I just think to myself, derivatives are limits, and all the properties of limits that we had are going to pretty much apply when we're talking about the limits of, or the taking the derivative and using rules there. So when we're doing this, the sum and difference rule says if I have addition and subtraction, okay, I would just take the derivative of each piece and add or subtract those derivatives, which would just be the same thing as saying f prime of x plus or minus g prime of x. It's two different functions. Okay, so let's do a big kahuna example of a sum and difference. This is a polynomial function. It has 1, 2, 3, 4, 5 terms, a degree of 3, fractional exponent, all the things. So we're just going to take the derivative. To find the derivative function here, we are just going to take the derivative of each piece. So I want you to pause me and come up with your derivative function on your own. And then, of course, unpause me so that I can show you the right answer. But I need you to think through this problem before I just spoon feed you the information, team. Okay. All right, now that you've had a chance to think, I'm going to do this in 2 steps because, again, I don't need to see these 2 steps, but I want you to understand that this is what's happening. I'm going to apply the constant multiple rule here. So this would be 10 times the derivative of x cubed, which would be 3x squared. Again, the exponent comes down. The power decreases by 1. Minus 12 times, okay, now I have 2x to the first, plus, okay, now look at this one, team. 7x is just a linear term. It's just like, if I graph 7x by itself, it'd just be a line, so that derivative is 7. Now, if you're like, Ms. Bowman, can I do the power rule here? Absolutely you can, because the exponent is 1, and that just turns into 1x to the 0, which, my darlings, x to the 0 is 1. 1 times 1 is 1, and I just end up with 7. I'd rather you think about it as a linear term and understanding about linear functions as opposed to using the power rule when it's x to the first, but it might be helpful later on. Okay, and then I have 11 times. Now, this is a fractional exponent. Actually, I probably wouldn't have seen that. It probably would have looked like that. Okay, so just so you know, sometimes we have radicals or fractions that are just x power rules in disguise. So I'm going to say 1/2 x. Now I'm going to have to do 1/2 minus 1. The fastest way for me to do that in my brain is just to do 1 minus 2 is -1/2. And then the derivative of 9, since it's a constant term, would be 0. So then if I clean that up, I end up with 30x squared minus 24x plus 7 minus 5.5x to the -1/2 plus 0. I'm not going to write. The only thing I will say to you, my darlings, is that with this term, okay, a lot of times they're going to put that in just a non-negative exponent form. So if we were to rewrite this one, it would be 5.5 over x to the 1/2. Or you could say 5.5 over the square root of x, or you could have seen it as 11 over 2 root x. All of those forms would have been acceptable for that. I just need you to be able to recognize those forms. Okay. Now, before I go on, I just kind of want to talk a little bit about just like some power rule disguises. So I know I didn't leave you a lot of spaces here, but I just want to make sure that we talk about this. So wherever you can add this on to your thing. Okay, so if I gave you f of x equals the cube root of x, and you're like, how do I find the derivative of that function? You need to rewrite this in exponential form. So that would just be x to the 1/3. Oh. I call that calculus-friendly form, or getting an expression ready for calculus. Get ready for calculus is what I call rewriting that. And I usually just say Graphica because, you know, acronyms are cool. So if I Graphica this, this function is the same thing as x to the 1/3, so that when I take the derivative here, I would bring the 1/3 down, and then 1/3 minus 1, 1 minus 3 is -2/3, and that would be the function. And then if you want to clean it up, the x to the -2/3 is going to join the 3 and become 3x to the 2/3. And we're okay with radicals in the denominator and that kind of thing. All right, another one. Let's say I gave you the function 3 over x squared. Okay, that looks like a rational function, and it is, but if I were to go ahead and find the derivative of this, I can rewrite this to become 3x to the -2. Again, I call that Graphicaing an expression, getting it ready for calculus, putting it in a polynomial form where there's no x's in the denominator and there's no more radicals. It's why on the summer packet, the first like 8 questions were like, rewrite this without a radical or without a fraction. Okay, so then if I find the derivative here, the 3 is a constant multiple. X to the -2 is going to become -2x. Now be very careful here, my loves. I'm going down by 1. -2 minus 1 is -3. So I end up with -6x to the -3, which if I put it back in algebraic form is -6 over x cubed. The 6 does not have an exponent, only a negative exponent, only the x does. So you only bring down the x term. Okay. Now, if we were to find the derivative of e to the x, let's use the formal definition. The limit as h goes to 0 of e to the x plus h minus e to the x over h. So it's f of x plus h minus f of x all over h. If I were to do that, one thing I could do to help myself is break that first expression up as e to the x times e to the h minus e to the x over h. So now I have the limit as h goes to 0. Notice that we have an e to the x in common, so when in doubt, I can factor out. And I'm going to pull it out of the whole thing, and I end up with that. Now, my darlings, this is why I don't like doing the formal definition of e to the x. You do not know what this limit is. What I would say is that you can graph it, you can look at it, and find the limit graphically, but by definition, the limit of e to the h minus 1 over h is 1. So if I take the limit as h approaches 0 here, I'm going to get e to the x, because there's no h there, times 1, so it's e to the x. So the derivative of e to the x is e to the x. Okay. If I had something that's not e to the x, let's say I wanted to find the derivative of a to the x, where a is a number. Now notice the big difference here between exponential functions and polynomial functions. In a polynomial function, x is the base and there's a number for the exponent, like x to the 4th. Those are power rule situations. If I have a number as my base and x as the exponent, that is an exponential function. It has a different rule. Now, if I were to prove this one to you, it would be very similar to the proof that we just did here, except I would have to use a change of base rule in order to get this e to the h minus 1 over h. When I do the change of base rule, I end up with an extra ln of a. So the derivative of a to the x is ln of a times a to the x. So it's slightly different than e to the x because it's base a. Now you're like, Ms. Bowman, are you really just going to do that and not tell me how or why? Yes, I am. I am going to do that. And am I going to ask you to memorize this rule? Yes, unfortunately, I am. We have about 16 derivative rules that we are going to have to learn, and we just learned 6 of those 16 today. So you have the constant, you have linear terms, you have power rule. Oh, that's what the page was missing. I was wondering there was a page missing. That was just the derivative of a constant. Maybe not. I thought I had another page in there, but I'm going crazy, guys. Okay. So let's do an example of the exponential functions, and then that's going to be enough rules to last you for the first day. But if I wanted to find the derivative of this function here, notice that I have an exponential piece plus another exponential piece. So I'm going to take the derivative of each piece. Now this first one has a constant multiple, so I'm just going to do 3 times the derivative of e to the x, which is just e to the x, plus the derivative of 2 to the x would be 2 to the x times ln of 2, or you could say ln of 2 times 2 to the x, either one. But anytime the base is something other than e, you have to use this rule right here. So I'm just going to say the a is 2, and it would just be itself again times the ln of whatever a was. And that would be, now I'm just going to rewrite this because it bothers me so that it doesn't have parentheses there. And again, I like to put the little ln in the back. A lot of people like to put it in the front. So sometimes you might see it written as 3e to the x plus ln of 2 times 2 to the x. Either way, that is your derivative function. Okay, so those are 6 derivative rules. You no longer have to do the limit definition of the derivative unless I formally request it. Otherwise, you are free to use the rules as we learn them. So we're going to be learning throughout this unit how to find the derivative of literally every function that we studied. Okay, so let's do a couple applications and then we'll be done for the day. This first one, find the equation of the tangent line to the graph of y equals 4x cubed minus 5x at the point 2, 22. So anytime I see write the equation of the tangent line, I'm thinking to myself, what do I need for the equation of a line? I need a point and I need a slope. So these are like, do I have my information? So I have my point right here. Do I have my slope? No. So what I need to do to find my slope is find the derivative function. The derivative function is the slope calculating function. So if y is equal to 4x cubed minus 5x, I'm going to find dy dx, or what we can say y prime. I'm just going to use dy dx to flip it up. So if I take the derivative of this function, it's going to be 4 times the derivative of x cubed is 3x squared minus, 5x is linear. Its derivative would just be 5. Okay, so my derivative function would just be 12x squared minus 5. Now, a derivative function is not the slope of a tangent line, okay? The slope of a tangent line has to occur at the point 222. So this is just a function that will calculate the slope. So now I'm going to find the value of that function at x equals 2. So notice I use the slope notation so I can teach you how to show that you're about to plug in. It's different than function notation. So if you use dy dx, then you have to draw a line and put x equals 2. If I would have said y prime, then I would have just said y prime of 2. Okay, but because I use dy dx notation here, I'm going to write it like that, and then I'm going to plug into my slope function. So we end up getting 4 times 12 is 48, minus 5 is 43. There's my slope. So now I can write my line. Y minus 22 equals 43 times x minus 2. And then I'm done. I could also ask you for the normal line, you know, that line that still exists that we haven't talked about in a while, but there's your tangent line. Okay, a couple more and then we'll be done. Higher order derivatives. So last unit we learned that there's such thing as a first derivative, and then I was like, oh, and there's a second derivative. And so in the world of slopes, we can actually keep finding the derivatives of each slope function until we can't anymore, and those are called higher order derivatives. So if f of x is my function, I would say f prime of x is my first derivative, f double prime of x is my second derivative, and then I could keep going. F triple prime of x is my third derivative. Now, if I wanted to take the derivative of the third derivative, it would be the fourth derivative. We don't put 4 primes because now it's just ridiculous. We kind of you'll either see it written in Roman numerals like that, or you'll see it as a little 4, okay? And that just means the fourth derivative. So if I wanted to find the first 4 derivatives of this function, you're like, oh my God, Miss Bowman, seriously, what are you thinking? But you'll see. I'm just going to take the derivative now. I do see some constant multiples here, but I'm going to go ahead, because this is like the 4th time, I'm going to go ahead and just apply that rule. So my first term would be 20 if I multiply those two things together, x to the 4th, plus 8x to the 3rd, minus 3x squared, plus 2x is linear, it becomes a 2. 8 is a constant, it becomes 0. There's my first derivative. Now, if I wanted to find the second derivative, I would just take the derivative again. So it would just be 80x cubed plus 24x squared minus 6x, and then 2 is a constant, it's going to become 0. So now I find my third derivative by taking the derivative again. 240x squared plus 48x to the first minus 6 because that's linear. So then my fourth derivative, and again you can use Roman numerals or put like a little 4 in parentheses. Okay. We put it in parentheses or else it looks like a power. So if you're going to use the numeral 4, then make sure that 4 goes in parentheses. Otherwise use Roman numerals like that, and you would be fine. Okay. So this would be 480x plus 48, and then minus a 0. So you can see we could keep going until eventually we get down to a constant, and the derivative of a constant would be 0. So I think I could take 2 more if I wanted to. It's usually 1 more derivative than degree because it'll get rid of your constant, unless it has an exponential piece because that will go on forever. All right, last application today, and then I'm going to take a break before I film my second video for you, back to back to back. Let's talk about another application. So horizontal tangents are places where the slope is 0 in a graph. So in a parabola, that would be like the vertex. If it's a cubic function, it could have 2, right? Or it could be a cubic function that looks like that. That would have 1. Okay, if you are looking for horizontal tangents, you are looking for where the slope is 0. Okay, so if I ask you to find those places in the graph, you're going to have to figure out where is the slope equal to 0. Well, to do that, you should find a slope function. The slope function calculates the slopes. So if I go ahead and do that here, if I can, multiply, right? 6 times 2 is not 16. 6 times 2 is 12, x to the first, plus 9 minus 0. I have this. This is a slope function. The derivative is a slope function. It'll calculate the slopes for me. So if I want the slope to be 0, I'm just going to make the slope's value equal to 0 and figure out what x in this expression would give me 0. So I'm going to pull out a 3. I end up with a quadratic. That's kind of nice. I can factor that. I'm going to set each of those expressions equal to 0. 3 is never going to be equal to 0 because it's a constant. But then if I solve this, -1 would make that factor 0 and -3. So there are 2 places where we have horizontal tangents here at x equals -1 and x equals -3. Now, if I wanted the points, I'm going to have to go back to the OG. Okay, so if I plug, I'd have to plug -1 into the original function to find the point at which that happens. So -1 plus 6 minus 9 minus 11 is 6 minus 21 is -15. So that point would be -1, -15. If I did that at -3, okay, that's going to give me -27 plus 54 minus 27. Oop, that makes 0 minus 11. So that point would be -3, -11. Okay, so the points are always going to go back to the OG. The slopes are you always use the first derivative. And that are your first set of rules. So congratulations, you are done.